Going to be doing chapter 8, number 3. The question was a bead slides without friction around a loop-the-loop. The bead is released from a height h equals 3.5 r. There are two parts. Part A is what is the bead speed at point A, and part B is how long is the normal force on the bead if its mass is 5 grams. Alright, for part A, you're going to be using the total mechanical energy formula, which is Kf plus V final equals K initial plus V initial. And K final is the kinetic energy, and V final, or this is U, sorry. This is U final, U initial. The U is the gravitational potential energy. The equation for K kinetic energy is 1/2 mv final squared plus, and the equation for gravitational potential energy is mgy equals 1/2 mv initial squared plus mgh. So this is your equation for part A, and basically you already have the height equals 3.50 r. So then you can use that to plug into. You can use that to plug in later on. So basically now you just use algebra and solve for V final, which is this. So now this cancels out because the initial is always 0 at the beginning. And then you can cancel out all the mass because it's equal everywhere, so it could be mass crossed out. So now just move everything to one side and leave V final on one side. So you have V final squared equals GH minus GY. V final squared equals GH minus GY times 2. And V final equals square root of 2 times GH minus GY. And you can simplify that even more by taking out the G, so it'd be GH minus Y. So here's the equation for V final for part A. So now all you have to do is plug in H for this. So you get 2G 3.50R minus 2R. And Y is 2R because it is going to be going around the whole circle. So it'd be from the top to the bottom is 2R. Now, you can simplify this even more by making it square root of 3GR. And that would be the answer for part A. Alright. Alright. Now for part B. Here's the picture of the force. So you have a little circle right here, or half of the circle, and the bead will be right here. So basically, normal force would be pushing down, but at the same time, mg would be pushing down. So that would make the force of y equals n plus mg, because we can change the x and y coordinates to be like this, making making everything positive going in the bottom, going in the down direction. So this would equal to mv squared r from Newton's second law. And we basically use that equation to solve for the normal force. So basically it would be, we would take everything and move it to one side, making normal force on its own side. So it'd be mv final squared over r minus mg. And then you can take out the m from both sides, so it'd be, or from right here, so it'd be m parentheses v final squared over r minus g. And then from that, we know that v final squared from part A is square root of 3gr. So m equals 3gr, but since it's squared, the square root goes away, leaving just 3gr minus g. And then taking that away, you could take out the r, so it'd be m3g minus g equals, or since the mass is 5 grams, we need to change it to kilograms for newtons. So 5.00 grams, and there's 1,000 kilograms in grams, so it would be, or 1,000 grams in 1 kilogram, I believe. So it's 1 kilogram here equals to 0.005 kilograms. So back to this equation, it would be 0.005 kilograms times 3 times 9.8 meters per second squared minus 9.8 meters per second squared. And that will total up to 0.098 newtons in the downward direction. And that is basically the way chapter 8, number 3 is done.